Okay, it is September the 12th, 2021. And I got a funny little goofy video for you tonight, just for fun. Here in El Paso at least, we have been just eat up with mosquitoes. So I bought this little mosquito, or bug zapper. Actually, seems to work quite well. There's the brand name of it. I'm not trying to sell it, or I'm not associated with it in any way. Drop it in the charger, and right there it charges. And you can put it right there and turn it on just by the press of the button. See a little red light come on, or you can turn it on and leave it on. And it works. Pretty amazing. Well, anyway, the spec sheet on it says that there's 3,000 volts between the outer grid on both sides and the inner grid. Well, you know what? Let's just measure it. I've got a meter right here with a times 100 probe. It's I don't remember what it is for 10 megohm inputs. It's a gigohm resistor in here. It works very, very well. We'll test our meter first, make sure it is accurate. I've got a power supply right over here, this little Keithley power supply right down here. I've got it run up to 999.99 volts, so we got 1,000 volts here. I'll show you what 1,000 volts looks like on the meter. It's actually pretty darn good. See, 1,000 volts measures 993, because everything's multiplied times 100. So it'll be 993.5. That's less than 1% error, so we can't argue with that. And then if we measure the voltage across this thing, and I don't believe this meter is going to load it down very much, because it is better than a gigohm. We put our negative side to the outer grid. See if I can do this without popping it too much. And then we touch this to the inner grid. If I could do it without shorting it. Whoops, now I'm shorting it. That's okay, that's okay. Look at there. 3,836 volts. Hope you can see that. Whoops. Oh, it's focusing and everything. 3,800 volts. I am impressed. Okay, 3,800 volts. And you can see the kind of popping that it does when you short it here. It's got a snap to it. I bet it would bite. It's pretty rough on the bugs, I'll tell you that. Okay, so what I thought I would do now, and what I've been trying to do, and I think I've about got it figured out, is I'm using a current probe, something that we could measure a very short and fast current, a Tektronix probe. So I'm just hooking, you got to be able to see exactly what I'm doing here. I'm hooking one side of a wire. This is just a wire. There's nothing special about this. It's just a convenient thing I had. I hook it to the ground lead, and then as I short this to the inner one, I'm measuring the current with this Tektronix current probe going through the wire. Just ignore this black wire, that does nothing. So you see what I'm doing, and as I do this, I'm shorting it, I'm sending a pulse through this wire, and we're measuring it with that current probe. Now, here's where the kind of tricky part is coming in. Let me get over here. I'll have to scope in here so you can see, excuse me, so you can see this. Having a tripod is great, but sometimes it's a problem in itself. Okay, let's get right in on that thing and look at it real close. This is kind of hard to see. Now I've got my probe set up to 10 milliamps per millivolt, but our scale is 2 volts per division. So if it's 10 milliamps per millivolt, then it'll be 20 amps peak, 20 amps per division. So it's like real current. Okay, so let's see if we can do this and capture it So you can see what I'm doing here. Yeah, there, that was a decent one. I hope you're seeing that. Yeah. Well, if I keep doing it until I get kind of a consistent pulse, there's one. Depends on what all I'm touching it to. Anyway, it seems like about the average. Seems like it's bigger now than it used to be. Oh yeah, it's quite a bit bigger. Well, from peak to peak, that pulse is now quite a bit bigger than it was. Oops. Yeah, this is the tedious one. Okay, it's going off the top. I don't want to get over here and burn up a whole lot of time doing this, but let's say it's 1, 2, 3, 4, 5, 6. Wow, no, it's actually going quite a bit higher than it was a while ago for some odd reason. Maybe it's because I opened and closed the, move that down just slightly. See if we can get that whole thing. We'll recalculate, it's easy. Hope you're actually seeing this. Now, you don't get it every time, just when it's kind of hard to get it to trigger. Well, bam. Now that I've moved the trigger point somehow. I don't think we'll be able to sync on it at all right there, but let's see. Well, now I'm not seeing anything. Well, I'm sure I've got to do a normal trigger. Let's see, now I'm not. Okay, well, now I can pretty well see the top of it. Got to catch it just right and getting it to trigger properly is the chore. Okay, let's suppose it's going the whole shebang from top to bottom. That's 8 divisions. That would be 2 20 amps per division times 8. That'd be 160 amps. I know that sounds absurd, but it's only 400 nanoseconds wide, or even more narrow than that, because see, we're at 200 nanoseconds per division, so it's a very, very tiny, short-lived pulse, very, very narrow pulse. Okay, I hope this is making sense, and I hope I'm doing some of this right. I'll do some of the recalculations, and what we're going to do is determine. Here are the simple little formulas. I was measuring 60 amps a while ago, and I did 3,800 volts times 60 amps times 400 nanoseconds. Let's do it again. Let's do it from peak to peak. However we want to measure this thing. If we do 3,800 volts times 160 amps, 160 amps, that's 608,000 watts, but we're only doing it for 400 nanoseconds. 400 E9 change sign times, that says we have 0.423 joules of energy. 0.243, okay? 0.243. And the capacitor is equal to 2 times the energy divided by the voltage squared, the capacitance value. A while ago I was getting about 12.6 picofarads, but if we do it like this, 0.243, enter that 2 times, enter 3,800 squared divides. Now it says that that'd be about 33.6. See, that's 10 to the minus 8, 3.3 to the minus 8. If we move the decimal place over 1, we'll get it in nano. Well, that's right, I was looking at it wrong a while ago. That's nanofarads. Okay, 33.6. Call it 34 nanofarads. 34 nanofarads, okay. 34 nanofarads is a 0.034 microfarad. So it looks like to me that capacitor in this thing must be rated at about 4,000 volts. Must be about a 0.034 microfarad capacitor. Would you believe that? 0.03? 0.04? Whatever. You know, this is a wild guess, but with a little bit of science mixed in with it, I think. Yeah, I'd believe that. 0.04. 0.03, 0.04 microfarad capacitor is what they're charging up, and that's what's discharging across the bugs, and it is just blasting the soup out of them. Well, that was exciting, huh? Well, anyway, yeah, the current is staggering, but the time frame is very, very short. So there you go. If I made some really stupid errors here, and you guys see that I did it wrong, please let me know. I copied these out. It started there. They called energy. They called it W. I don't like W because that's watts to me. I call it E. Is QV over 2. Q's the charge in coulombs voltage, which is also 1/2 of the capacitance value times the voltage squared, 1/2 CV squared, and then you get down here, you get C is equal to 2 times the energy in coulombs divided by the voltage squared. That's what I just did, and came up with that this number right here, 33.684 times 10 to the minus 8, or it'd be 33.684, 33.6 or 37. 34 nanofarads or 0.034 microfarads. That makes more sense because a while ago I read it wrong. I came up with 12.6 picofarads, and I said that's just, I think it's bigger than that. So basically what they're doing is charging up about a 0.03 or 0.04 microfarad capacitor and discharging it across those little bugs. Anyway, all for fun. Thanks for watching. Stay safe.